Let's take a look at another example. One of the primary products produced at Kruger Industrial Smoothing is a line of gears. The gears are used in an aircraft, and the gears in general should not weigh less than 1.62 ounces. A quality control engineer at Kruger inspected a sample of 17 gears and recorded the weight of each in ounces. Let's use a p-value approach to address this set of hypotheses. Okay, so what are we going to focus in on here? They cannot weigh less than 1.62 ounces. Okay, so our null and alternative hypotheses, they cannot weigh less than 1.62 ounces. Weigh less than 1.62 implies less than. It's a less than statement. Does not imply equality. Okay, the less than statement has to be in the alternative because equality is always in the null. Okay, so right here, a barbed wire tattoo. Okay, barbed wire. And then underneath it, it says equality must always be in the null. Okay, remember that. Equality must always be in the null. So what's our null statement? It has to include equality. The mean is greater than or equal to 1.62 ounces. Okay, and here we want to know, is the mean less than 1.62 ounces? Okay, if it's less than 1.62 ounces, then we have a problem. So that's what we want to key in on. Okay, so we go out and collect a sample of size 17. We have a Y bar from that 17 samples of 1.617 ounces and a standard deviation of 0.005 ounces. Okay, so the uninitiated, someone who hasn't had a stats class, would say, well, 1.617, that's less than 1.62, so we should reject the null. But you know better than this, right? We have to account for the fact that this was a sample in the first place. Y bar is a random variable. It follows a sampling distribution. So we can't just directly compare these two numbers. We have to account for variability, sample size, and confidence whenever we draw this conclusion. Okay? So we're going to use the p-value approach here, so we need to calculate the test statistic. The test statistic is, of course, y bar minus mu naught over s over root n. Okay? How different is the sample evidence from the hypothesized value in standard deviation units? Okay? So that's how we're accounting for variability here. We are dividing by the variability to see how different these two are, accounting for variability. Okay? So we can input this in, 1.617 minus 1.62 divided by s over root n. Okay? And if we work that out with the calculator, we should get 2.474. Okay, what does that say? That says that this number lies 2.74, that's a negative, lies 2.474 standard deviations away from this to the left. Okay, so that gap is actually pretty big. It doesn't look very big, but it's actually 2.474 standard deviations. That's almost 2.5 standard deviations away from this value. Okay, so that's why this is so important to account for variability whenever we're drawing this kind of conclusion. Okay, so now we want to find the p-value. And the p-value is going to be in the lower tail, right? This is a one-tail test in the lower tail. And we're going to plot for t for degrees of freedom 16. We're going to plot our test statistic, negative 2.474, right here. And that area, that's entirely the p-value. Okay? Because this is a one-tail test in the lower tail. Okay, that's just one of our decision rules for whenever we calculate the p-value. If we see a less than here, the p-value is entirely in the lower tail to the left of the test statistic. Okay? So what is this tail area? Well, since we have a different t distribution for each different degrees of freedom, we're probably not going to find the tail area for this thing exactly using our t-table. Okay, but we can kind of produce a set of bounds. So if we go and look at the row degrees of freedom 16 in the t distribution table, we'll see this. for t of 16, we'll go down and see negative 2.120, okay? And that has area 0.025, okay? So the tail area associated with negative 2.120 is 0.025, okay? And we also have this value right here. This is negative 2.583, okay? That's also, again, one of the entries in the row associated with degrees of freedom 16. This area down here, okay, is 0.01. And we know that our test statistic lies in between. Okay? So our test statistic, which is negative 2.474, it lies in between negative 2.120. This is greater than, sorry, that's the other way around. Okay, whoops, no, that's okay. Here, okay, our test statistic lies between this value and this value. Okay, that means that the p-value, this area down to the left of this, okay, that area down there must lie between 0.025 and 0.01. We don't know what it is exactly because we don't know where exactly that number lies, but the area must lie between this number and this number, okay? So it must lie between 0.01 and 0.025. So our p-value here is pretty small. We don't know exactly what it is, but we know that it lies between 0.01 and 0.025, okay? That would give us a pretty strong conclusion. That p-value awfully small. It would be smaller than most alpha levels that we would consider, okay? So with this kind of p-value, most likely we're going to reject the null and conclude that indeed the ounces of these gears is smaller than 1.62 ounces. Okay, that's a bad thing that might lead us to implement some changes to the gear production process. Because again, this is a small p-value, we're going to reject the null. Okay? So this assumes that you have the t-table that you're provided, or that's in the back or the front of any common stats textbook. But if we have Excel, we could also find this exactly. Okay? And we could do that with the tdist function. Okay? The tdist function. Okay? The tdist function reads in the value on the axis. Okay? In this case, that would be our test statistic. It then reads in the degrees of freedom, and it reads in the number of tails. Okay? If we put in a negative value into the value on the axis, if we were to put in this value directly, it's going to give us an error. Excel does not like to read in negative values for the test statistic. So we have to enter in 2.474, and it will give us the area of the upper tail up here. And we just use our symmetric knowledge here to conclude what the p-value would be from that. Okay? So we input this in Excel as 2.474, the value on the axis that we want the area above the tail for, degrees of freedom 16, and a one tail, okay, the upper tail. Okay, if we were to do this, we get a value of 0.0125. Okay, as it turns out, 0.0125 is in between these two values. Okay, so we could bound it. That doesn't change our conclusion, right? This is a sufficiently small p-value. Even the upper bound is still quite small. We would reject the null. Also, we could find it directly, okay, and that itself is also a very small exact p-value. We're still going to be rejecting the null. The conclusions here aren't going to change. It's just a matter of, do we want to bound the p-value, or do we want something a little more exact? Okay? On the exam, you may not have access to Excel, so you may have to just bound based on the T distribution table, and that's okay. Okay, you know how to do both of these now. You're on a desert island, you don't have Excel, you only have your textbook. This approach works just fine.